Hello everyone, I hope you're all healthy and doing well. Remember last time we covered improper integrals and that finishes the theory part of integrals that we're going to learn in this course. So in this video and the next two videos, we're going to learn about applications of integrals. What do I mean by applications? We're going to use a definite or improper integral to find a geometrically meaningful quantity such as areas of regions, volumes of solids of revolution, arc lengths of graphs of functions, surface areas of solids obtained by rotating graphs of functions around an axis, and so on. Okay, so in this video we're going to cover section 5.7, which is areas of plane regions. As I said, we're not going to learn any new theory, so we're simply going to interpret what we have already learned in a specific setting. So let me start. Areas of plane regions. So let F and G be continuous functions over an interval AB with f(x) less than or equal to g of x for all x in AB. Okay, so pretend that I have two continuous functions on the closed interval AB, such that one of these continuous functions is less than or equal to the other one on the whole interval. Then the area of the region R between the graphs of F and G over the interval AB is, okay, suppose that I want to find no, I don't want this. I want this other shape. It should be fine. Suppose that I want to find the area of the following region. This is y equals g of x. This is, let's say, y equals f of x. And let's say that this is a and this is b. I want to find the area of the region R between the graphs of these functions over the interval AB. So what do I mean by this? I mean the region which I'm shading right now by blue. Okay, for some reason this is automatically creating, okay, I think it was because I chose that option. Okay, so I want to find the area of this region R. How do I do that? Now, the area of this defined area under the curve y equals g of x over the interval AB is given by the definite integral of a g over AB. Okay, so this gives me this whole area. But I want to get rid of the area of this region. Well, the area of that region is the definite integral of f over AB. Okay? So if I take this difference and if I integrate that difference, that should give me the area of this region R. Okay? And it doesn't matter whether f and g are positive or negative. Like in this picture, I drew the picture as if these are positive functions, but this is not necessarily the case. These can be negative. They can be both negative. One of them can be positive, the other one can be negative, and they can just go up and down around the x-axis. It doesn't matter. If you take this difference and integrate this over this interval, then you're going to get the area of this region. Okay, so this is my top function, and this is my bottom function. So if you have two functions, and if one of them is greater than or equal to the other one, if you take the difference top minus bottom and integrate that difference, then you're going to get the area of the region between graphs of these curves over the interval AB. Okay, and note the difference. I'm not saying the signed area, I'm saying the actual area, okay? Because this difference is always going to be positive. This difference is always going to be non-negative because you're looking at the difference top minus bottom, okay? Top function by definition is greater than or equal to the bottom function. So this is non-negative, so this integral is a non-negative. And this is the area of R, okay? So this is the area of R. Okay, so I have this. Now, in general, even if we do not have f(x) is less than or equal to g of x, or g of x is less than or equal to f of x over the interval AB, we can find the area of the region between y equals f of x and y equals g of x over the interval AB by the integral okay. Now, on this picture, we have the top function, we have a bottom function, so we're assuming that one function dominates the other one over the whole interval. What if this is not the case? What if we have something like this? Maybe I choose this one now. Okay, let's put it over here. And let's say that this is y equals f of x, and this is y equals g of x. Now, what if the picture is like this? It's not the case that one of these functions dominates the other one. They just go up and down. They're maybe like intersecting on one interval. One of them is bigger on the other. On some other interval, the other one is bigger. So how do you compute the area of this region? Okay, the area of the blue region. Now, pretend that, okay, let's work this backwards. I claim that this definite integral gives me this area. Why? Let's look at this picture. What's going to happen over this interval? Let's say that this is A and this is C1. On the interval A, C1, F is bigger. Okay, as you can see from the picture, f is greater than or equal to g, which means that this quantity f minus g will be positive, so it's going to come out from the absolute value as is. So it's going to be like I'm going to have integral from a to c1 f of x minus g of x. Okay, and then this will give me the area of this region by this observation here. Okay, now what's going to happen over the interval? Let's say that this point is c2. What's going to happen on this interval? Then on this interval, g is bigger than f, which means that this is going to be negative f minus g. So when I try to get rid of the absolute value, it's going to come out as g of x minus f of x. Okay, and then on this interval, the top function is g, the bottom function is f. So I have top minus bottom integrated over an interval c1, c2. So I get that this is the area of this part of the blue region, and over this interval, this is going to come out of the absolute value as f minus g, so it's going to give me the area of this region. Now I add these integrals, I'm going to get the integral of the absolute value of f minus g from a to b. The point is, this quantity, absolute value of f minus g, no matter what interval you choose, this is going to always give you top minus bottom, top function minus bottom function. Why? Because if f is bigger than or equal to g, if f is greater than or equal to g, then this is going to come out as f of x minus g of x, because this is not negative. If g of x is greater than or equal to f of x, then because this is negative, it's going to come out of the absolute value as g of x minus f of x, so it's still going to be top function minus bottom function. So when you integrate this, this will always give you the area of this region. Okay, so if you have two arbitrary functions, if you want to find the area of the region between the graphs of these over some interval, then what you do is you subtract these functions, you take the absolute value, and because you're taking the absolute value, it doesn't matter which one you subtract from. So choose one, like consider the difference, take the absolute value, integrate this over your interval. This will give you the area of the region between the graphs of these functions over that interval. Okay, so this is my A, this is my B. Okay, so that's that. Now let's see this in action. I'm going to solve 3 questions. Okay, this section is this is a small section, so I don't need to spend too much time on this. Oh, one more remark. These claims. Okay. Maybe I should just write this after the first question. Yes. Let me solve the first question, then I'm going to write a remark, then we're going to solve a second question involving that remark. So, example. Find the area of the region in plane bounded by y equals x squared minus x and y equals 3x plus 5. Okay. Okay. So I'm supposed to find the area of a region in plane, and the region that I'm given is apparently the region bounded by 2 curves. Which curves? Y equals x squared minus x and y equals 3x plus 5. So one of them is a parabola, the other one is a line. So let me first try to draw a picture so that I can actually see this region. So this is these are my coordinate axes, The curve y equals x squared minus x, it's a parabola where the roots are 0 and 1. Okay, so it's going to be a parabola like this, and these roots are going to be 0 and 1. Okay, and then the line y equals 3x plus 5, it's going to be something like this. Okay, y equals 3x plus 5. Now, maybe I should just put it over here, and yes, this is better. 3x plus 5. It's going to look like this. Now, the region bounded by these, because I'm using the phrase bounded, I'm supposed to find the region which does not extend to infinity. The region bounded by these two curves is this one. Okay. Okay. So how do I find the area of this region? Okay, I need to first find these points, because at the end what's going to happen is I'm going to see this region as region between graphs of two functions over some interval, and then when I try to find this area I need to take a definite integral, but then I will need that interval. Okay, that interval is not 0, 1, because as you can see this region is between the graph of this function and the graph of this function over this whole interval. So I need to find that interval. In order to do that, we need to first find the intersection points. Okay, so we first find the intersection points of these curves. So how do you find the intersection of these two curves? You try to solve these together. This is minus x. You try to solve these equations together. From this, you're going to get that x squared minus x is 3x plus 5. So x squared minus 4x minus 5 equals 0. So you're going to get x minus 5, x plus 1 equals 0. So you're going to get x equals 5 or x equals a minus 1. Okay, so this point has x coordinate minus 1 and this point has x coordinate 5. Okay, okay, thus the area of this region is, now this region which is bounded by these curves, it's a region which is stuck between graphs of two functions. Which functions? F of x equals x squared minus x and g of x equals 3x plus 5 over the interval minus 1 to 5. Okay, so what I'm going to do is I am just going to, now look at this, I'm going to take the difference of these two functions. I'm going to take the absolute value of that, and I'm going to integrate this from minus 1 to 5. Okay, now in order to get rid of the absolute value, I need to figure out which function is the bigger one over this interval. But from the picture you can actually see that that function is f(x) equals 3x plus 5. So I have the top function minus the bottom function integrated from minus 1 to 5. Okay, and this gives me the area. And you can easily take this integral. This is 3x squared divided by 2 plus 5x minus x cubed divided by 3 plus x squared divided by 2. Evaluate at these points. Dot, dot, dot. Okay, you can just plug in and subtract. I'm not going to do that. Okay, so that's that. So let's solve another question. But for this question, before we solve this one, I'm going to write down a remark. One is allowed to have a equals minus infinity or b and or b equals plus infinity in a one is allowed to blah 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 in the claims above. When I say the claims above, I mean these. Okay. Now over here, I pretended as if a and b are real numbers, and I'm working with a bounded interval. That's not necessarily the case. Well, we learned about improper integrals, okay? So you're allowed to have you can do the exact same thing with an unbounded interval. You can pretend that a is negative infinity, so you're integrating from negative infinity to something, and you can allow b to be infinity. Okay, so you can do that. Maybe you have two curves, and the region between them is not bounded, but it extends to infinity, so you may have to integrate from minus infinity to plus infinity. That's fine, because we learned about improper integrals. What I'm saying is that I'm just allowing I'm allowing a and b to be negative infinity and positive infinity respectively. Similarly, these claims hold even if these integrals are improper. Okay? Pretend that you're still working with a bounded interval, but you do not have continuous functions. Okay, maybe your function is not continuous at one of the endpoints. Maybe it looks like this. Okay, so it's not continuous here, and it blows up around a. Maybe you have an improper integral. We learned about improper integrals. These claims still hold. Okay, so the point is, I wrote these as if I'm just working with definite integrals, usual definite integrals. All these things can be generalized to improper integrals as well. Okay. The point is, f and g need not be continuous over the closed interval ab. It suffices for them to be continuous on the open interval ab. And if you in that case, you would say that, okay, if they're not necessarily continuous on the closed interval, these integrals may be improper. Well, what I'm saying is, let them be. Okay, that's still fine. Example. Let's see an example. Find the area of the region between a y equals, I have a question. Yeah, 2 over 1 plus x squared and y equals a 4 over 4 plus x squared. Okay. Similarly, these claims hold, blah blah, improper, and f and g are continuous only on the AB. Okay. Let's put it over here. Okay. Now, in this question, we will have to deal with improper integrals. You'll see why in a second. Now, the question is of the same type. Find the area of the region between blah blah. I'm given two graphs of functions. Okay, I should first plot these. Now, plotting these is not as easy as plotting these functions, which were a linear function and a quadratic polynomial. Like one of them is a parabola, the other will give one of them will give me a parabola, the other one will give me a line. So I was able to plot these very quickly. Now, for this question, you have to plot these functions. I'm going to directly do it without telling you how, because we already covered a section on this. Remember, it was 4 something, sketching graphs of functions. So go back to that section, study it if you forgot how to sketch graphs of functions, and realize that when you sketch the graphs of these functions, what's going to happen is one of them will give you, maybe I should plot this like that. One of them will give you something like this. Let's say y equals 2 over 1 plus x squared. There is some inflection point over here which I'm not finding, and at the plus infinity and minus infinity, this has like when x goes to plus infinity, this approaches to 0. When x goes to minus infinity, this approaches to 0. So I have this horizontal asymptote, and its maximum values obtained at 0, which is 2. Okay. So this one will look like that. Now, this is bad. I should draw the other one first. Let me draw the second one. But this needs to be, nope. Okay, I'm so good at drawing this. It's gonna look like this. Yeah, this is how the graph of this function would look. Okay, and this is the point 1, and here's the point. The other one will look like this. Okay, so this is y equals this is y equals 2 over 1 plus x squared. Okay. Now, why do the graphs of these functions look like this? That's an exercise. Okay, so exercise using the techniques that we learned before, double check that the graphs indeed look like this. So double check that the graphs actually look like this. Okay. Now, I want to find the area of the region between these curves. But the region between these curves is actually not a bounded region. It extends to infinity. Okay, it actually extends to infinity. So it goes like this, which means that when I need to integrate to find the area of this region, I need to integrate over an unbounded interval. So I'm going to have an improper integral. Okay, and this remark says that like whatever we did over here is actually like these are all true for a these are all true in the cases where we end up having improper integrals. Okay, so in particular over here I can have a to be minus infinity, b to be plus infinity, and so on. So let me write the following. The area of the region between these curves is, now I'm going to integrate the difference of the absolute value of the difference of these functions over which interval? Over the interval minus infinity, infinity. Okay. Now, in order to evaluate this, okay, how do we evaluate this integral? I just wrote down an improper integral. How do we evaluate this? I need to get rid of the absolute value first, and in order to do that, I need to figure out which function is bigger on which interval. Okay. Now, from the picture, like if you actually double check that the picture looks like this, you will see that there are like two intersection points. There are 2 points where these curves intersect. So I need to find them. In order to evaluate this integral, we need to first find the intersection points. Okay, so let's do that. This is creating a problem over there. Let's put it over here. Nope. Let's put it over here. Yes. Okay. So let's find the intersection points. If you try to solve these equations together, you're going to end up getting 2 over 1 plus x squared is 4 over 4 plus x squared. So from this you're going to get that 8 plus 2x squared is 4 plus 4x squared. So you're going to get 2x squared equals 4. So you are going to get that x equals plus minus root 2. So I have plus minus root 2 here. Okay. So now I know which function is the top function, which one is the bottom function on which interval. On the interval minus 2 to 2, minus root 2 to root 2, the top function is 2 over 1 plus x squared, and the yellow one, 4 over 4 plus x squared, is the bottom function. And over the interval, root 2 to infinity is the other way around, and so on. Okay, now that I figured this out, I can actually evaluate this improper integral. First, let me open the absolute values up. Over the interval minus infinity to minus root 2, the top function, the function which is greater, is 4 over 4 plus x squared. So this difference, the absolute, like this is negative, so when it comes out of the absolute value, it's going to come out as negative. So these signs will flip. Okay, so I have this, and over the interval minus root 2 to root 2, the bigger one is 2 over 1 plus x squared, and this is the smaller one. And over this interval, root 2 to infinity, again, the bigger one is 4 over 4 plus x squared, so I have top minus bottom. And that's that. Now, the rest is an exercise for you. I'm not gonna evaluate these. Like, this video is not about improper integrals, it's about areas of plane regions. So remember, if you haven't watched the last video, just go and watch that, learn how to evaluate this and how to evaluate that. Okay, and you can easily find the, let me tell you the antiderivatives for these functions. This is supposed to be 2 arctangent of x over 2 plus c, and this is supposed to be 2 arctangent x, okay, plus c. So use this fact to evaluate these integrals. Okay, let's double check this first one. What's the derivative of this? This is 1 over 1 plus x squared divided by 4 plus x squared. Yes, 4 plus x squared times, no, I think this is incorrect. What's the derivative of this? Derivative of arctangent of 1 over 1, derivative of arctangent of x plus 2 is, oh no, that's correct, yes, this is correct. Anyway, use these antiderivatives to evaluate these improper integrals, and this is a proper one, so you use one term of calculus directly and get the answer. Okay, you're gonna get a finite answer. Okay, it's not just because this region extends to infinity does not mean that it has infinite area. It's going to be a finite one. So that's that. Okay, one more thing. Sometimes one more question, and the point of this question is to illustrate you the following. Okay, what have we done over here? Let's go over what we have done. I had two functions, which I assume to be continuous over the interval AB, and I said that, okay, if f is less than or equal to g, then this area is supposed to be the definite integral of g minus f, because definite integral of g will give me the area of this whole thing. The definite integral of f will give me the area of the small part, and now I'm going to subtract these. Okay, and then I said that if you just look at if it's not the case that one function dominates the other one, then just take the absolute value of the difference, and what's going to happen is on different intervals, this will automatically, when you open up the absolute value, it's going to give you the top function minus the bottom function. So you're going to get the area of the region between these two graphs of functions over this interval AB. And then we solved the question, and then I said that, okay, you didn't have to deal with proper integrals there. This actually, the whole thing actually applies to improper integrals as well. Okay, so you don't have to assume that f and g are continuous over the closed interval. They may be continuous on the open interval, so you may have an improper you may have some improperness at one of the endpoints like this. It doesn't matter. or maybe a and b are negative infinity and positive infinity respectively, so you have improper integrals of the first type, all these remarks still apply, okay? In the, I should say claims, remarks above. Similar, these remarks hold, blah blah blah. So we have that. Now, I'm going to tell you another way to generalize what we did over here. We pretended all the time that our regions are regions between graphs of functions of x. But sometimes, like you may end up dealing with regions which are between graphs of functions of y. Okay, in that case, y will be a function of x. Okay, even if you're dealing with functions of x, sometimes it's easier to pretend that your region is between graphs of functions of y, and in that case, what's going to happen is you're going to interchange the roles of x and y. Instead of integrating with respect to x, you're going to integrate with respect to y. Okay, and then everything will work out. So let me write a remark. So this is like another remark. Sometimes it is convenient to work with convenient to interchange the roles of x and y, that is, see the region a, as a region between the graphs of functions of y over an interval for x. In this case, we simply integrate we in this case sometimes convenient interchange roles of x and y, blah blah, graphs on functions of y. In this case, we proceed as before. After changing the roles of x and y in the integrals in the above remarks. And when I said the above remarks, I mean the whole thing I wrote at the very beginning. Maybe I should like solve a question so that what I'm meant over here becomes easier to understand. So I had one question. Find the area of the region bounded by x equals y squared minus 2y and x equals 4 minus y squared. Okay? So, before I write down any solution, let me first sketch this region. Now, over here, I have the curve x equals y squared minus 2y. Okay? Now, if you interchange role of x and y equals x squared minus 2x, this would be a parabola with roots x equals 0 and x equals 2. But I have x equals y squared minus 2y. So this is a parabola, but it's as a function of, this is a function of y, whose graph will be a parabola if you pretend that the independent variable is y and the dependent variable is x. So what I mean is this is a parabola which would look like, okay, if you interchange roles of x and y, if I had this, I would have this parabola, okay? But over here, I don't have y equals x squared minus 2x. I have x equals y squared minus 2y. So what's going to happen is I'm going to take this picture and flip. So I'm going to get a parabola which would look like this, okay? So this is x equals a y squared minus 2y. And these points, you can check that, are 0 and 2. And similarly, if you were to plot y equals 4 minus x squared, you would get this picture, but I have x equals 4 minus y squared. So what's going to happen is I'm going to take this picture and flip it with respect to the diagonal. So I'm going to get the following picture. X equals 4 minus y squared, okay? And let me quickly find these intersection points. I know that I'm going to need them. So, I mean, one of them is already clear. It's 2, because when you plug in 2, it's satisfied. The other one is y equals minus 2. Okay, so no. This is wrong. This is 2y squared minus 2y equals 4. So y squared minus y minus 2 equals 0. So y equals y minus 2 plus y minus 2 times y plus 1 equals 0. So this gives you y equals 2, which I already had, and the other one is y equals minus 1. So this is minus 1, okay? Oops. This is minus 1. And you can easily find the x coordinate by plugging in y equals minus 1. This is 5, okay? This is 5. Now, let me solve this question in the wrong way. Well, it's not really wrong, but in the I'm going to do a solution which is theoretically correct, but it's going to be very long and you don't want to do that. And then I'm going to do another solution, a shorter solution, which would explain why I wrote this remark. Okay, now there is a way to get the area of this region using these formulas that I wrote, which involve integrals with respect to x. And here it is. A the longer solution. And here it is. I'm going to see this region as a region between graphs of functions of x. Okay, how am I going to do that? I'm going to split this region into 3 parts. Okay, like this. And then this region is the union of this part, and maybe I should just color these differently. so that I can talk about these later. So I have this part, and I have this part, and let's not use yellow, it's already used, and I have, okay, and another color, this part. Okay, now the area of a the area of the orange region is the area of the orange region is the area of the orange region is equal to. Now, this piece over here is between the graph of this function and this function, which I can actually find for you. One of them is going to be I try to solve for x in terms of y. You're going to get that. Let me do this quickly. Because this is the incorrect solution, this is the solution that you're not supposed to do, I'm gonna do the computations and erase them, okay, because I don't want you to do this solution. So try to solve for y in terms of x, add 1 to both sides. Okay, then this is 1 minus 1 squared, this is x plus 1. So you are going to get y equals plus minus a square root x plus 1, okay? And this part will be a, maybe just I should just explain this one. No, never mind. I don't want these to be in the notes because then you're going to try to do it like this, and I don't want that, as I said. Anyway, this part is the graph of 1 plus squared x plus 1. This part is the graph of 1 minus square root x plus 1. So the area of that region is a, again, y equals 1. This is minus 1, okay? You can actually check that that's a minus 1. The area of this region is integral from minus 1 to 0. The top function, which is square root, 1 plus square root x plus 1, minus the bottom function, which is 1 minus square root x plus 1 dx. Okay, so that's that. Now, the area of the green region, where's my green? The area of the green region, is equal to, now I have an integral from 0 to 5, okay, and the top function here in this case is, well, try to solve for x in terms of y in terms of x. It's going to be like x equals 4 minus y squared, so y is a plus minus square root 4 minus x, okay, and this part will, this part will be y equals square root 4 minus x. So here my top function is square root 4 minus x. Something is off here. This is not, I don't think this is 5. Wait, what? No, something is off. This doesn't make sense. Something is off. Let me figure out what it is. Hmm. I think my intersection point is wrong. Let me find the intersection point again. Let me find the intersection point again. It's -1. When you plug in y equals -1. Oh, it's 3, not 5. I can't even do simple subtraction. Oops. Oops. Now this is 3. Okay. So this integral is up from 0 to 3, not 5. Now it makes sense. Anyway, and this is my top function, and what's the bottom function? It's this one, and I already found that it was okay. I'm gonna have to do it again. This is because I just erased it. Y minus 1 squared is x plus 1, so it's a y equals 1 plus minus square root x plus 1. So my bottom function is 1 minus square root a x plus 1. Okay. So you can check that this curve over here is the graph of this function. And then this is the area of the green region. And finally, for the last one, the area of the yellow region. This equals, I'm just going to write this down because I've already lost so much time on this. This integral is from 3 to this 1y0x is 4. So this is from 3 to 4. This is from 3 to 4. I'm going to directly write down those functions, okay? There are 4 minus x under square root minus, this is the top function, the bottom function is minus square root 4 minus x dx, okay? So this part is this function, this part is that function, and this part is the function, and this part is that one, and this part is that, and this part is that. Now this is, as I said, the incorrect solution. It's not incorrect. Like find these integrals, add them up, we will get the area. But the point is, I shouldn't, like, there's an easier way. I shouldn't have done this. Why? Why did I have to do this? Because I insisted using the formula that I learned as is, like as an integral with respect to x. In order to do that, I need to see this region as a region between graphs of functions of x and so on. But this region, by its own nature, is not between a like without any splitting. I can see that see this as a region between graphs of functions of x. So I need to split this region into 3 parts, and for each part I needed to find a separate top function and bottom function, and then I subtracted these, I integrated, and so on. You saw what happened. But I could have simply done the following. Okay, let's name this the easier solution. This region, if I try to see this, like I'm asking myself the following question. Okay, if I try to integrate, if I at the end want to integrate with respect to x, then I need to see this region as a region between graphs of functions of x and so on. So I need to split this into three. Can I see this region as a region between graphs of functions of y? And the answer is yes. This is actually how it is given to me in the first place. Okay? So this region is the blue region is between the graphs of functions g of y equals 4 minus y squared and f of y equals y squared minus 2y over the interval minus 1 to 2. Okay, so take this whole picture, flip it. Okay, this region is between graphs of functions of y, g of y equals y 4 minus y squared and f of y equals y squared minus 2y over the interval minus 1 to 2. Okay, so its area is, now I'm going to do the exact same thing that I have been doing, except I now am going to interchange the roles of x and y. Now my interval is the interval, you see, my y values go up from here to here. So I'm integrating from minus 1 to 2. So my y values are changing from minus 1 to 2. And what is my top function in this case? The top function is this one. Okay? And this is the bottom function in this case. Okay? Just take this picture, flip it, like rotate this in 90 degrees counterclockwise, and then you'll get that. I can actually do this for you, but I'm not sure whether I want to. Like, rotate left. Okay. And let me also flip this horizontally. Oops, that's not good. Anyway, y increases in that direction now. So what's the top function? It is it's g of y equals 4 minus y squared, and the bottom function is f of y equals y squared minus 2y. Okay. So I have a integral of top minus bottom. And that's it. So this will give you the area of this region. You see, if you try to write this region with integrals that are with respect to x, then you have to do this computations. It just takes, you have to split this into three parts. For each part, you have to figure out the top function and the bottom function. Like, it's going to take a while. But if you try to see this as a region between graphs of functions of y over some interval, then this is like, it's very easy. It's a single integral. Okay. So what this remark says here is sometimes it's convenient to do that, okay? Just because I give you a region and tell you to find this area doesn't mean that you should always use integrals with respect to x. Sometimes it's easier to use integrals with respect to y. It depends on your region. I can give you certain regions, I can give you some regions so that whether you use x or y doesn't matter. You end up having to split that region, okay? And I think you're going to have such questions in your recitation, so let's stop now. Stay safe. I'll see you later.